So this is an event in a series of events that we are organizing this year on Shaky. And in fact, this is a concept that came about between a collaboration of our society, IEEE Robotics and Automation, with AAAI. And I would like to ask Raja Shatila, our president, to come here and little bit discuss how this happened and about all the events, related events that are taking place.
Thank you, Usama. Thank you all for being here. This is really a unique event. And what we decided to do with AAAI, a sister society on AI, is to reunite robotics and AI together again. You will see this in the Shaky pictures and the talk that will be given by Peter. But we wanted also this to be an endeavor of the two communities to really team together to advance this exciting topic of intelligent robotics systems. And we decided to give grants to students to attend AAAI and vice versa, students to come to ICRA from the AI community, and to organize this event where you will see several highlights about Shaky, of course, which was the first project on that, and also the presentations of students that has been made from robotics into the AI, AAAI in January, and from AI researchers in our conference here today. And we'll have also a panel later after the keynote speech, so please don't miss it. Thank you.
Thank you, Raja. So if you really want to know about all the history about Shaky, you are in the right place. Shaky was one of the first autonomous robotic system that attempted to bring together all the aspects of perception, planning, reasoning, and reasoning about actions and acting as an intelligent entity. Well, we have here a number of people, the pioneers, Peter Hart sitting here next to Nils, and I had the pleasure to really come to know about the AI Center at SRI and all the work that has been going on there. I'm just delighted to introduce Peter, who will start this event with a presentation about Shaky, the history. Peter, please.
Well, thank you so much for inviting us here. It's really quite a treat to be here 50 years later. So I'd like to tell you a story. And this is a story about how a group of researchers were inspired by a brilliant physicist named Charlie Rosen to do something that had never been done before. We wanted to build the world's first mobile intelligent robot. So I'll tell you how it got launched, how we approached this new world of robots, some of the things we did, and what the consequences have been on both current technology and really all of our everyday lives. And along the way, I'll show you a few reactions that people had to this world's first mobile intelligent robot. So here's the proposal that launched it all, submitted by the Artificial Intelligence Center of Stanford Research Institute to DARPA just 50 years ago, very early days for computer science. You can see we proposed developing intelligent automata for reconnaissance. So reconnaissance was the application, but the research motivation, and this was Charlie Rosen's inspiration, was to build an experimental test bed for integrating all the areas of artificial intelligence as then understood. So knowledge representation and reasoning, planning, machine learning, computer vision, even natural language understanding, we wanted to put that all together for the very first time. Well, here's Charlie and the automaton, as he used to call it. I think maybe out of concern that if we called it a robot, nobody would take us seriously, because until then, robots literally were works of fiction. But pretty soon, Charlie and all the rest of us called it a robot. Here's Shaky in a little more detail. We put the drive wheels on the side so we could steer by pivoting. And we drove them with stepping motors so we could count the pulses and use that for dead reckoning. Those stepping motors probably accounted for the shakiness that you may have seen in the video. Our main sensor was a low-resolution video camera for which we had to build our own analog to digital converter because there were no frame grabbers. And we augmented that with a homemade laser rangefinder with a rotating mirror in that upper housing and a receiving lens below the video. All the computation was done remotely on a time-shared mainframe, and Shaky communicated over that radio link, and you can see it has a little ground plane under the antenna. We had little wire touch sensors and later added a push bar to push things around. And the whole thing was powered by Sears truck batteries. There were two ground rules behind this design. The first was that we wanted to minimize mechanical complexity, and so we never mounted an arm, although that was discussed. And the second is that we didn't want to spend effort on miniaturization, and that accounts for Shaky's blocky shape. Basically, it's an electronics rack on wheels with a sensor assembly on top. We were very aware of Shaky's limited mechanical and sensory capabilities, so we designed a correspondingly simple experimental environment consisting of some half-dozen rooms, and we populated the rooms with these large geometric objects that Shaky could push around. The color schemes were chosen so that Shaky had a chance of seeing some of the edges while still reflecting enough light for that laser rangefinder to work. Our first computer was an SDS 940 time-shared machine, an early time-shared mainframe. And in looking at it, I realized that its main memory is about half the size of the L2 cache on this laptop. A few years later, we upgraded to a much more powerful DEC PDP-10, and at that time, we embarked on a major rewrite of Shaky's control software while making only minor changes to the robot hardware. So I'll describe this version 2 of Shaky. Well, that was the physical setup. Now let me focus on the AI and software issues that were the main topic of our research. There were two big ideas behind version 2. The first was to represent Shaky's world by statements in the first-order predicate calculus. And here you see a fragment of the model showing where Shaky is, the fact that door D1 is open, meaning it wasn't blocked by an object, and so on. This predicate calculus model was a major expansion of a map-like model that we used in version 1 that was based on a grid where we used variable cell sizes for reasons of computational efficiency. So that was idea 1. The second big idea was to structure Shaky's control software into these 4 layers. The bottom 2 layers, the low-level and the intermediate-level actions, were programmed by us, and they did things like get Shaky to a given location, or get it through a doorway, or push an object. We showed the intermediate-level actions in their own layer because all of them were structured as Markov tables. And here's the Markov table, slightly simplified, for getting Shaky through a doorway. The way you interpret these tables, as you recall, is you scan down the left column until you come to the first true condition, and then you execute the corresponding action. After that, you loop back to the top. So this one starts out that if Shaky's in front of a door and it knows the door's not blocked, then it calls another action called bumble through, which makes little course corrections if Shaky bumps into a side and tries to get Shaky through a doorway, and so on. An important property of these Markov tables is that they're inherently persevering. Because of this looping behavior, they keep trying to do something useful until they either accomplish that or they hit a hard failure. And that turns out to be a very key property, as you'll see in a moment. But if this were the end of the control software story, Shaky would be very limited in what it could accomplish. It would only be able to achieve goals that had been foreseen by the developers and for which there was a pre-programmed solution. So, of course, no self-respecting intelligent robot should be limited to pre-programmed canned routines. And so, to go further, Shaky has to be able, on its own, to construct a sequence of pre-programmed actions to create a new plan to achieve a new goal. That's the job of STRIPS, the Stanford Research Institute problem solver. That's the next layer up in the software stack. So STRIPS came about by combining two hot topics of the day. The first was means-ends analysis, a problem-solving strategy that was used by Newell and Simon in their pioneering general problem solver. And the second big idea was resolution theorem proving in the first-order predicate calculus, introduced by J.A. Robinson and then applied by Cordell Green to building question-answering systems. Richard Fikes and Nils Nilsson combined these two ideas to create STRIPS, which applies means-ends analysis to predicate calculus representations. And that was a key reason to move to that new model. A little later, we figured out how to generalize STRIPS plans by replacing constants in the plans with variables. So, for example, a short plan for Shaky to block, say, a particular doorway with a particular block was generalized to a plan to block any doorway using any block. We also invented these data structures called triangle tables to represent the internal structure of a plan, and in particular, how the steps of the plan depended upon one another. And this formed the basis for our plan execution executive we called PlanX, which was the top layer of Shaky's controlled software. So using this software machinery, PlanX could monitor Shaky's real-world execution of a plan. It could detect if something was not going according to plan, and if so, it could replan from that point, reusing any portions of the original plan that might still be applicable. And this was critically important. We recognized at a very early stage that there was a big difference between planning for a physical robot that has to execute plans in the real world where things often go wrong, and planners up to that point, like the general problem solver, that just had to print out a plan on paper and then it was finished. And so this plan execution executive, together with those persevering Markov tables down at the intermediate level action layer, were our solution to the problem of robust real-world execution. And there was a bonus to these generalized plans. Shaky could learn them in the sense of storing them for use by STRIPS as actions that could be used in future planning problems. Well, that's something about the control software. Let me move on and tell you about two particular algorithmic developments that turned out to be important. The first is in the area of computer vision, and it has to do with our development of what I'll call the modern form of the Hough transform. So the story is that in 1962, Paul Hough patented a very clever transform for detecting collinear points in images. But there was a major drawback, and the drawback is that Hough's transform space was unlimited in extent because of the problem of infinite slopes. So of course that's computationally very inconvenient. A little later, I was trying to get ideas from an obscure branch of 19th century mathematics called integral geometry, and I learned that mathematicians had good reason for using something called the normal form of a line that involves sines and cosines that I had never seen before. But I saw that if we swapped out Huff's linear transform, for this sinusoidal one, we get a tightly bounded, compact transform space, and as you know, that's what's been used ever since. And Dick Duda and I also figured out an extension to be able to detect curves in images as well. So that was one of several things we did in computer vision. The other area is navigation. Of course, Shaky had to find its way around, and so we developed a number of shortest path algorithms. Nils Nilsson and Bert Rayfield and I developed one that we called A star that we thought was super cool because we could mathematically prove that it had two very desirable properties. First, it always works. It will always find the shortest path. And second, it's computationally efficient in the sense of considering the smallest possible number of choice points or nodes in its search. Well, of course, we were eager to break into print with what we thought was a great result, but uh-oh, here's a rejection letter from the most prestigious journal of the day, politely telling us to go peddle our manuscript somewhere else, which we did. And Bert Rayfield, a co-author, I think, was so annoyed at this that he co-founded a journal to avoid, was it the AI journal, Bert? To avoid this misunderstanding. But we finally got it accepted by transactions of the IEEE, which at the time was so low prestige that I used to call it the IEEE transactions on miscellany. But it eventually got noticed. Well, those are some of the things that we did. What were some of the reactions to this? Here's a very popular magazine of the day running a cover story on co-ed dorms. And inside there was a big spread on Shaky by a journalist named Brad Darrick. I don't know if you could read the subhead in the back, but I think Brad hyperventilated just a bit. The subhead says, "The fearsome reality of a machine with a mind of its own," and he called Shaky the world's first electronics person. But while some like Brad thought that AI and robots would take over everything, there were skeptics. Bert Dreyfuss at UC Berkeley argued that AI was not just difficult, but on deep philosophical grounds, he claimed that it was in principle impossible. And one sunny afternoon, I trucked up to Berkeley to debate Bert in front of, I remember, a standing room only audience in a big UC lecture hall. And the only thing I can tell you is after 2 hours, neither of us had made a dent in the other person's convictions. And somewhere in between these two guys were labor union leaders who visited us, and they worried that robots might someday take manufacturing jobs. And of course, they eventually proved to be correct, as you see in this graph of the installed base of manufacturing robots worldwide. Some other reactions came from visitors. A teenage Bill Gates drove down from here in Seattle to California with his buddy Paul Allen to see Shaky, and decades later he remembered thinking how cool it was. Arthur C. Clarke came by just after the movie 2001: A Space Odyssey came out. And I think Shaky did everything Shaky could do. And I think Arthur recognized it would take a while before we caught up with HAL 9000. And then there was a US government auditor who dropped by my office, and he started questioning me. He said, "Is it really true that you have taken delivery of 8 billion and something or other packets of bits?" And he wanted to know had these packets arrived in good condition and whether there was any tarnish or corrosion on any of those bits. Well, that's the way it was back then. Here we are now. What's happened in between? Has Shaky made any permanent, had any permanent impact? The answer is yes, quite a lot, as you can see in this quote from James Kuffner, who's on the program later this afternoon. He said it is truly amazing how both in terms of architecture and algorithms, the Shaky project was ahead of its time and became a model for future robot systems for half a century. So Shaky's had a significant impact, not just on current technology, but as I said, really on all of our everyday lives. And there's a half a dozen different areas where we can trace Shaky's impact, and I thank Nils Nilsson for these many examples. So the first is layered control structures. I mentioned that we were, of course, the first to apply it to robots because it was the first mobile intelligent robot. Architectures derived from that have been used in any number of modern robots. Sebastian Thrun used it in Stanley that won the Grand Challenge 10 years ago, and the Monterey Bay Aquarium Research Institute uses it in their current underwater robot that's going on right now. Next, I emphasize the importance of robust real-world execution and how that really is a defining difference between robots and many other areas of artificial intelligence. Any number of modern robots use execution methods that are derived from Shaky and also from the work that Nils Nilsson and his students did at Stanford in the 1990s, some follow-on work on teleoreactive programming. Two robots that use that style of execution are Willow Garage's PR2, which we've seen all over the conference here today, and a kind of a spin-off from Willow, Savioke's Savvy1, which, if you haven't seen it, is a commercial robot developed by Steve Cousins to provide hotel room service. Next, something called adaptive cell decomposition. I mentioned how in version 1 of Shaky, for computational efficiency reasons, we used a grid with variable size cells. In other words, put the resolution just where you need it. That's believed to be the first use of what's now called adaptive cell decomposition. And I think you know that's now a standard approach in robotics, as you can see in this quote on the left from Wu Lai and Chen about cell decomposition methods in robot path planning. And it's also a standard method in 3D form in computer-aided design, as you see in this excerpt from a recent text on CAD-CAM. Next, the area of strips and what are called strips rules. A key concept in the strips robot planner was the use of what are called strips rules to represent the logic of an action. There are three parts of them: the preconditions that have to be true in order to employ an action, then things that are no longer true, and things that become true after the action is taken. This particular design approach has been used by any number of subsequent planners, and here's a little genealogy chart from Sheila McElraith showing many subsequent planners that have used strip-style rules, and you can also see it from the huge number of hits that this gets on Google. Strips rules are also used to plan the actions of what are called non-player characters in many video games. The next area is heuristic search and the A* shortest path algorithms. Once we finally got it published, the A* paper seemed to inspire many variants and elaborations. There was early on a bidirectional search A*, search from both ends towards the middle, hierarchical A*, where you plan freeway routes cross-country at a high level and local routes at a detailed level, memory-based A*, where you save solutions for future use, and many others. Right now on Mars today, a variant called Field D* is used to navigate the Curiosity rover. So thinking back to that first proposal where we proposed applications to reconnaissance, I don't think any of us anticipated this particular reconnaissance mission. Back here on Earth, when you have your driving directions computed by a web service or by your car's GPS or your handheld, it's a good bet that some version of A* is doing the heavy lifting. A* is also used to plot the paths of characters in many video games, and it's also used in quite a few parsing applications. And finally, our version of the Huff transform has been used for many, many years in all sorts of visual inspection applications in manufacturing. But recently, it started to appear in the last couple of years in automobiles. I took this shot of the dashboard of my car where there's a feature that tracks visible lane markings in order to alert the driver if the car is drifting out of lane without signaling. In this case, they call the feature lane keeping assist. So this is now actually becoming common in quite a few quite a few automobiles. Well, to wrap up, here are some of the people who made Shaky. Some key figures like Nils Nilsson and Len Chaitin, who are both here today, are not in the picture, but there on the left is Charlie Rose, and next to him is Burt Rayfield, who's here today. I'm in the back with my mustache. Dick Duda's in the back, and down front is Richard Fikes. And in the very front is Helen Chan Wolf, who I think has a pretty good claim to being the world's first robot programmer. So I like to think of Helen as being the Lady Ada Lovelace of robotics. Here are a few of us today. You get extra credit if you can match this picture up with the previous one. Of course, getting Helen right doesn't count. Nowadays, Shaky lives in the Computer History Museum in Mountain View, California, where it's the centerpiece for the museum's exhibit on AI and robotics. And Shaky's also a charter member of the Robot Hall of Fame at Carnegie Mellon University. So what did we achieve? Personally, less than I had hoped. Perhaps less than many of us hoped. And really that wouldn't be surprising given the just enormous scope of our ambitions. But I do think we achieved more than any of us could have appreciated or recognized at the time. So that's our story. 50 years ago, we took a big swing at a big problem. Back then, it took a team of PhDs to get Shaky to do anything interesting. Nowadays, I see that robots are programmed by 11-year-olds. So it's a kind of reminder that we invest in basic research for the same reason that we plant trees, to benefit future generations. Thank you. I really appreciate your warm response, but I'd like to offer I'd like to offer one comment that I've observed over decades, that behind the people that get the recognition, there's a team of unsung heroes. They made it possible.
So before the next part of this event, we're going to take a few questions, and there will be also a panel later on. We will be able to develop more questions. But just those who would like to ask questions, there are microphones here in the front. So please make use of the microphone. Could you come to the front, please? Or someone could take the microphone. Well, let's find a robot that will take the microphone over there. Switch it on manually, please.
Hello?
Yes.
Well, quick question. That's why I wanted to ask it back there. How do you see the future? What do you think? How do you see the future of AI? What's the vision for the next 50 years from your perspective?
It's working, I think. Or is it then let's use this one.
Well, I'm very optimistic. I think the progress just in the last 5 or so, maybe 10 years has been just astonishing. We're all very aware that there's a prominent current of concern about the future of AI and what it might do, and I think that has to be acknowledged as well. But from a technology viewpoint, I'm just very impressed with what's been done of late, and I wouldn't venture any specific predictions over a long period of time. I don't think any of us 50 years ago could have predicted what you see at the show here today or the talks here today. No.
All right, well, we'll continue with questions later after the panel. Now we are going to start the